Today we're going to start a somewhat different concept, so we're going to leave acids and bases for a little bit, but still equilibrium. We're going to talk about something called the solubility product, also known as KSP. And so what it entails is we've been talking salts, and so we have different kinds of salts. We've got like sodium chloride as a salt, and then we've got like silver chloride as a salt. If we go back to net ionic rules, we talked about how sodium chloride will always break apart in the ions, but silver chloride on the other hand will pretty much stay together. And so this is what we're going to be talking about, is how are these kind of different from one another. And so you may have heard the term solubility and saturated, and a saturated solution. For example, when you take salt, NaCl, and put it in water, it will dissolve, but there's a point where you will saturate the solution, and then even NaCl won't dissolve anymore. So there's every time you reach a point of saturation, no more will dissolve. So example, again, take that salt, put it in the water, you keep adding, eventually it's going to just fall down to the bottom, and that's reaching a point of saturation, which is what we're going to be kind of talking about here. And so dissolving of a salt, and again, when I say salt, it doesn't necessarily mean NaCl, what you put on your french fries. So does reach a point of equilibrium. There is a fill-in-the-blank note thing if you want to use it as you go along here. And so it says the salt is attracted to itself, which is why it can somewhat stay together, but also attracted to water molecules. So the water molecules will start to pull the ion apart, even NaCl. It tries it with silver chloride as well. So first we get the process called dissociation. So when I say dissociation is when it's pulling itself apart. But eventually, if you keep adding, you're going to get then that precipitation, which is the salt coming back together. And depending on what salt you're dealing with, some of them will saturate or start coming back together very quickly, where NaCl, you can put lots of NaCl in water before it gets too saturated, before it would start to precipitate. So the equilibrium is this dissociation and this precipitation occurring, and so that's when we reach this point of saturation. So saturation means we've gotten to a point of equilibrium. So that means where it's coming apart and going back together at about equal rates. So I would like you to know this word. If you see the word saturated, saturated is going to mean we are at equilibrium. So that way, if we're doing a rice table and you see the word saturated, you'll know to put that value at the E. Another term I'd like you to be familiar with is, some of our problems are going to say, calculate the molar solubility. So the molar solubility is how many moles per liter that particular substance can break apart. And so the best way for me to tell you is that's always going to be our X. So if it asks for molar solubility, you're going to be solving for X, which is the molarity required to saturate the solution. How much of the original substance, moles per liter, will reach a point of saturation. So that's kind of important, X. Alright, so let's look at how we're going to write some of those equations, and then we'll start some of the calculations. Alright, silver sulfate dissociates into ions. When the solution is saturated, the following exists. So this is that picture that we've got going on. And so I'm going to write the equation. So we've got Ag2SO4, silver a positive 1, sulfate a minus 2. And this starts out as a solid, so that's kind of important. For all these problems, you're going to have a solid. I'm going to put it in water, and I'm not going to write water in the equilibrium. And this does get to a point of equilibrium, so the arrows are going back and forth. So no more RICA for KSP. This is actually rice going on. So we're going to get some silver ions, and please make sure you always put the ion charge. That is a 1 plus or just a plus. But do you notice there are 2 of them? So you're going to get 2 silver ions. ions. And then you're going to get 1 sulfate ion when this thing dissociates in water. And these are both aqueous. Aqueous means dissolved in water. Alright, so there's my reaction. Basically that in water breaking it down. Looks very similar to how we did with the acids. You just break them down. There are coefficients now, so that's important. So the equilibrium expression is still a K. This one's now called KSP. We'll talk about why it's called KSP in just a second. And it's always the products over the reactants raised to their coefficient powers. And so you're going to have silver ions, but they're going to be raised to the second power because we always raise them to their coefficient power, times sulfate ions. Please always make sure you put that. And that's raised to the first power. You do not have to write 1. I was just doing it for emphasis. And then it would usually be divided by the reactant side, but we have a solid, and what are you not supposed to put in the expression? You're not supposed to put in solids. So you don't have a denominator here, so you just are going to basically be multiplying. And because you're multiplying in math, when you multiply two numbers, you get a product. So this is why this is called the solubility product, SP, solubility product, because it is the multiplication of the solubilities together. They will be getting raised to powers. So the math is really not that hard on these. It's not really that complicated. So let's look at just some practice. So for each of the salt, write a balanced equation showing its dissociation in water, and then write the KSP expression. So we have iron 3 hydroxide, iron 3 hydroxide. That's a solid. It's going to break down into iron ions with a positive 3 charge, because that's what the Roman numeral means, and then 3 hydroxide ions. These are both aqueous. And if we write the expression, KSP equals the iron times the hydroxide raised to the third power. Okay, super easy there. Alright, nickel sulfide. I really should have given a Roman numeral with that. Nickel 2 sulfide will do. And so that is Ni. Positive 2 sulfide is a negative 2, so that will look like that. That is a solid. You'll get some nickel ions, and you get some sulfide ions. And it's a 1-to-1 ratio. It's really nice when it's a 1-to-1 ratio. So your KSP is simply your nickel ions to the first power times your sulfide ions raised to the first power. Alright, so you see that's not too bad. Silver, positive 1, chromate is a negative 2. So that's a solid. You're going to end up with 2 silver ions. Silver's a positive 1. And 1 chromate ion, which is a 2 minus. So there is the dissociation equation, and there is the KSP. So the KSP would be silver ions squared times chromate ions. That's just the charge there raised to the first. And again, you don't have to write to the first. So there's the dissociation equation, and there's the KSP expression. Alright, let's go on and do some math. So it says the molar solubility of barium carbonate is 5.1 times 10 to the negative 5th at 25 degrees. They're going to give you temperatures, but you don't have to worry about the temperature. They're only giving you the temperature because these are only, the constants are only constant at a certain temperature. So you know that if you heat up water, you can make things more soluble. So 25 is typically room temperature. So our first order of business is to write our equation. So we have barium, which is a positive 2, carbonate, which is a minus 2, so we get BaCO3. You can see it down here. And then that's going to get you some barium ions Make sure you always have those charges on those ions, especially in lab reports. Alright, so there's my equation. I'm going to go ahead and write my KSP over here. So we're basically going to have barium times the carbonate raised to the first. That's a plus there. Alright, so I'm going to go ahead and do a rise table for you can see how this rows. These actually can be done without rise tables, but it's good to kind of set it up and see. So I'm going to just squiggle underneath that there. Okay, the reason I'm squiggling underneath that is because it is a solid. So it says barium carbonate has a molar solubility. Molar solubility, I told you a second ago, anytime they tell you that, they are giving you the X value. Because these would start out as 0 in the beginning. These are all going to be 0 because we're not going to do the complicated ones where you're putting them anything but water. We could, but for sanity's sake right now, we're just going to put them in regular water. Okay, so it is telling me how much is being added right here. And so it says, we would normally say, oh, it's adding X amount. Well, molar solubility is X. So they are giving me this value. And they're also giving me, this is a 1-to-1. Ratios do matter. Ratios do matter. So you've got 5.1 times 10 to the negative fifth. This one's also 5.1 times 10 to the negative fifth. So your KSP basically would be, if we threw it into this expression, would be both of those times each other. So can you see that that would be just that squared? Because it's going to be barium ions, which is that, times that ion. So it's basically just going to be squared. So I'm going to start making a connection with you on something, so because you'll start to see a pattern with these. If you see the pattern, you don't necessarily have to rise. When this guy broke apart, it broke into a barium ion and a carbonate ion. So it broke into 2 ions. Okay, 2 ions. And so if you have something that breaks into 2 ions, your KSP will always be X squared. So that's going to be a little trick that we can kind of use. So if it's got 2 ions that it breaks into, we can use X squared. Alright, let's move on. Example number 3. Let me go back to my blue. A saturated solution. So saturated, that's important. That means we're at equilibrium. Silver chromate has a silver ion of 1.3 times 10 to the negative 4th molarity. What's the KSP for silver chromate? Alright, we wrote that equation a second ago, and it looked like this. 2 silver ions plus 1 chromate ion. Go and get my aqueouses and solids in there. And we're just not going to worry about this guy under here. This does start out as 0. So they are not giving me X this time. They're not giving me X. They're giving me this value right here. They're giving me that value. So, well, that was 0. So that's how much got added here. The problem is, that's technically not what the other guy is. It's not what the other guy is because those coefficients are back. For every 2 of the silver ions, I'm only getting 1 chromate ion. So if this is 1.3 times 10 to the negative 4th, which is what it told me what that would be, this would be half of that. This would be 6.5 times 10 to the negative 5th molarity. If you took this number and divide by 2, that's what you would get. Remember at the C means change in, but you can think of C. Hey, make sure you use coefficients. So it's got to be proportional to the coefficients there. So now your KSP, this is very similar to what we did a couple units ago. Just regular rise problems. We had those coefficients. This is going to get squared. And then this guy's only getting to the first power. So our KSP is, I've only got 2 sig digs in this problem. 1.1 times 10 to the negative 12. I don't have to put a unit on this because it is an equilibrium constant. KSP is another K. It technically would be molarity to the cube if I had to give it a unit, but we don't have to have units for K's. So there's my solubility product for this reaction. Here's a question. What would that is the solubility product constant, but if I ask for the molar solubility of this one, what would it be? Remember, that's just X. Can you see that X would be just the 6.5 times 10 to the negative 5th? That would be our molar solubility of this. Basically, it's the ratio of this guy to those here. So it's always how much of this is breaking down, and this is a 1-to-1 ratio. So it's really what your X is every time. So that's what our X would be. As you work with these, you'll start to see that a little bit better. All right. It says the KSP of nickel 2 carbonate is 1.4 times 10 to the negative 7th. Calculate the molar solubility. Well, nickel 2 carbonate is NiCO3, solid. Positive, negative 2, you get nickel ions and you get carbonate ions. Do you see how many particles we got? We got 2 ions forming here. So we know that our KSP is X squared. And they're looking for the molar solubility, so they are looking for X. So basically I could take the square root of the KSP. So you could use this. I'm going to rice it because some students are like, oh, just can I rice it? Sure, we can just rice it. So, but you don't necessarily have to rice these to figure this out. So I'm going to show you. Alright, I know the K, but I don't know the molar solubility. So anytime you know the K, means you're going to have X's in your. So this is a 1, so it's a 1x. And this is a 1, so it's a 1x. So looky there. X squared equals 1.4 times 10 to the negative 7th. So then I would take the square root of both sides, and I would find the molar solubility to be 3.7. There's only 2 sig digs to get in here. 3.7. I used 3.74. I'm going to go ahead and do this because my next calculation is based on that. I got a sig dig error. You just have to take -1 off me. My next problem is based on this one, so I'm going to go ahead and go with that. So, well, here we go. We can fix that. There we go. Now we're fixed. So 3.74 times 10 to the negative 4th. That's our molar solubility. That's the amount of moles per liter that's going to saturate the solution. So number 5 is spinning off of that one. What is the mass that would make that molar solubility? The mass of nickel carbonate needed to prepare 500 milliliters of a saturated solution. Saturated solution means it's holding the most that it can hold, and then it's just going to drop to the rest. So saturated means equilibrium. How much? What's the molarity? So we need mass. So we've got our old friend of moles equals that molarity times liters. So here's our molarity, 3.74 times 10 to the negative 4th. We are looking for nickel carbonate. That is the amount that got subtracted over here. Can you see it? We just don't, it doesn't have a molarity, but it is the amount. So it's going to be the amount of moles. We could do a mole proportion and go with that, but I'm just going to tell you it's going to be the amount of moles. So we're just going to go your molarity times our liters, which is the 0.5 liters. Don't know what I've got going on there. And so we have a 1.87 times 10 to the negative 4th. That's how many moles. That's how many moles of your carbonate. So that's how many moles of your nickel carbonate there will be. So this is going to be your NiCO3. Oh, I'm going to run into a big black spot there. Let's write small. Alright, so then we've got moles of nickel carbonate going to grams of nickel carbonate. And with grams, you always do molar mass, 118.7 off the periodic table. And we get 0.0222 grams. Now, you're like, oh, okay, that's good. Got an answer. Woohoo. But here's the question. If you think about it, now everybody should have done with some scales at some point. 0.02 on a scale, that's like a speck or so. That's hardly any amount. And we're saying that if we put 0.02 in 500 milliliters of water, it's going to be saturated and fall to the bottom. Meaning you can hardly put any nickel to carbonate in water without it falling to the bottom, which is why we box nickel to carbonate. Okay, it's because it doesn't take very much at all, and then it's saturated. So we start seeing that precipitate almost immediately. So NaCl, lots and lots of grams we can put in before we saturate. But silver chloride, not so much. Nickel carbonate, not so much. That's not very many grams. All right, on we go. So it says to determine which salt is the most soluble, you compare the molar solubilities, which means you compare the X, not the KSP. Okay? Because, to determine whether an acid is strong, the stronger the acid, the larger its K value. And really strong acids don't even have a K value. You can't do that with molar solubility. You can't just look at these numbers and go, oh, well, that one is the smallest number, -73rd. That's insane, by the way. That's the smallest number, so therefore that is going to be the least soluble. No, you need to find the molar solubility, which basically means you need to find X. So I'm going to use these as a little pattern for you can start to see some things. Okay, so here's our page, and if you're pulling with the worksheet I've got, you should be able to see these. So I'm going to come to a blank page before we can work these. Alright, so I've got CuS, copper 2 sulfide, makes copper ions and sulfide ions. I won't worry putting the aqueous. This is solid, those are aqueous. Can you see that we have two particles? If we have two particles, remember what the KSB? KSB is going to equal X squared. We could do a Rice equation, you could see it. And substitutes go, oh yes, we need to see it. So can you see that we would have X, X, and X would equal KB. So therefore we could simply put in the 8.5 times 10 to the -45th equals X squared, and you could take the square root of both sides. And for this one, I get a molar solubility, and again, I'm going to use 3 sig digs, 9.22 times 10 to the -23rd. I may fix the sig digs before I upload the worksheet to you guys. Alright, so there's that one's molar solubility. Let's look at the next one. Silver 2 sulfide, silver sulfide. You're going to get 2 silver ions, and you're going to get 1 sulfide ion. I'm going to show you Rice, but there's a pattern to this one as well. There's my dog barking. Alright, so we've got 0, 0. Can you see that there's 2 here? So this is going to be 2x. This is going to be x. This is going to be 2x. And this is going to be x. So you're going to get your KSP here to equal 2x, then it's going to be to the second power, because we doubled it and squared it, times x. Alright, I'm going to do some simplification for you can start to see something. Okay, so anytime, let's talk how many particles we have here. How many ions do we just break into? There's 2 there and 2 there, so we have 3 ions. Okay, so if I simplify this, that 2 is also being squared. This is 4x squared. This is times x. I'm going to simplify a little bit more. You get 4x cubed equals KSP. That is the pattern for 3 ions in a KSP. So x squared for 2 ions, 4x cubed for 3 ions. So to solve this, well, let me get my value. We had 1.6 times 10 to the negative 9. Whoops, that is not 19. Negative 49th power equals 4x cubed. So you're going to want to divide by 4 first. And then I did not write what that equaled, I'm sorry. And then you're going to want to take the cube root. And I think on your calculators that's math 3. Math 3 is the cube root. Let me make sure I do have a calculator here. Yes, math 3 is the cube root. So then we will find the x to be 1.6 times 10 to the, nope, just kidding. I'm rewriting that problem. It is 3.42 times 10 to the negative 17th power. Alright, going to do the last one. So we had bismuth 3 sulfide, Bi2S3. When this thing breaks down, you get Bi, oops, did that wrong. It is a 3 plus charge. There are 2 of them, working backwards there. And you've got 3 sulfide ions. Again, these are all aqueous. So that reverse swap drop is what we're doing there. So that's a solid. I'm going to do the rice so you can see. You can always do the rice. Some people start to see the patterns. Okay, so 0, 0, you have 2x, you have 3x, you've got 2x, 3x. So your KSP is going to be, can you see how many ions there are? There are a total of 5 ions. I will tell you this doesn't always work, because I was thinking this pattern always worked with 5 ions. It is a 2 to 3 or 3 to 2. If it's a 4 to 1, this won't work. You'll have to figure it out. But this will work for a 2 to 3 or a 3 to 2 coefficient for 5 ions. So you're going to have 2x squared, and you're going to have 3x cubed. Let's do some simplification. That's 4x squared. That is not 9. That's 3 times 3 times 3, which is 27x to the third. So that gets to be 108x to the fifth. 108x to the fifth. So if it has 5 ions, do you see a pattern there with that? If I go back up, you might see a pattern with that one. And you might see a pattern with that one. There's a pattern to these. Is our KSP, and this one was 1.1 times 10 to the negative 73rd. To solve, I would go 108, divide by 108. And now you need to take the 5th root. To do the 5th root, you type in 5, and then you hit math 5, scroll down to 5. That's what telling it what route to take, and then you would enter in the number there, and I got this x to be 1.00 times 10 to the negative 15th. That is the molar solubility. So let's go back to our chart and let's fill that in. So we had a 9.22 times 10 to the 23rd molar solubility, 3.42 times 10 to the negative 17, and a 1.00 times 10 to the negative 15. So looking at the molar solubility, the amount of moles that will dissolve, this is the larger number here, the larger molarity. So this one is actually, believe it or not, the most soluble. That one up there is the least soluble. So you can't tell by looking at KSP. You actually have to find X for each one of those. Okay, and again, there was that pattern of KSP for this one was X squared. The KSP for this one was 4x cubed, and the KSP for this one was 108 x to the 5th. So there is a pattern for 4 particles. So let's see, let's make up something for generic. You're not going to have 2 and 2 because they would be canceling. I'm just going to make up a generic A, B, 3. Okay, so this will break down into some A ions plus 3 B ions. I just made up something. Just want to show you. This one would have 4 particles, so there is a pattern to it as well. Can you see this would be X and 3X, X and 3X, and you're welcome to use the pattern because I'd love you to see the pattern. So this would be X raised to the first. This is 3X raised to the third would equal our KSP. So your KSP would equal X. And if I simplify, this one is 27x to the third. And if I simplify one more time, that is, that is the pattern for 4 particles. Okay, so 4 particles or ions. This would be 2, this would be 3. This would be 5, but only if it's a 3-2. If it's a 4-1, it's different. I don't think 4-1s are very common, so I don't think that you have to worry about that. But I want to say an always, because there's not an always, so 4-1 is. So let me get to the end here. This is, if you decide to do those practice worksheets, this is the answers to those. So that is the KSP lesson. So if you have any questions, please email me.